Let's look now at an example of electronic circuits. How is it that we can model these circuits in such a way that we can later describe them with the equations of motion? So we'll begin first of all with the circuit. Here we have a couple of resistors, a capacitor or two, and we have some nodes that are open. We're going to try to measure voltage across these nodes, and in order to do that, we need to know a little bit about the current flowing through the various components. But first of all, what kind of components do we have and what are their values? Well, let's just go ahead and label it. We have an input source. We have two resistor values, R1 and R2. We can call that R sub I, actually. Then we have two capacitors, C1 and C2. I'm interested in measuring the output voltage, V sub O. So with these values, we can label our important nodes, A and B. So we're going to use A and B in terms of defining voltages with respect to ground, so that we can use the differences in those voltage and the components through which they flow to estimate current, according to the equations of motion. So, based on this, we'll delve back into the depths of our memory to determine if we can remember Kirchhoff's current law. We're going to use this to establish the equations of motion for this circuit in terms of the input and output voltages. So with this in mind, let's go ahead and define the currents coming out of node A. So the difference between V sub I and V sub A flowing through R1 tells us the current in this direction. But we're actually interested in summing all of the currents that are going out of the node. So instead of V sub I minus V sub A, we want the negative value there. We also want V sub A minus V sub B divided by R2. That tells us the current going from node A to B. And this is the current that's going from node A to ground through the capacitor C1. So C1 dVA dt. So all of these values, according to KCL, are going to be equal to 0. So that's our first equation. The second equation is not unlike the first. We're just going to be doing it at node B instead. So V sub A minus V sub B, that tells us the current going into node B. So the other current that comes into node B goes through capacitor C2. So that is, we're going to add now plus C2 dVi minus Vb, so we're subtracting the current across Vi and Vb, and then taking the derivative with respect to time. So that gives us the current going through C2, and the sums of all of these currents going in are also going to be equal to 0. So here we have our two nodes, and this gives us two equations with which we can describe the equations of motion for the system. So I'd like to rewrite these in terms of Vc1 and Vc2. I'm going to define those voltages however it is that I'd like. So I'm going to let Vc1 be the voltage at node A, and Vc2 be V sub I minus V sub B. So now I'm going to substitute for VA Vc1. Likewise here, I'm substituting Vc1 for V sub A, and then for V sub B I'm doing a little bit of math to move V sub C2 onto the other side. And that's going to give us, now we can just substitute for V sub A, Vc1, and all of those values equal to 0. And we can do a little bit of rewriting here to put dVc1 on one side. And if we'd really like to, we can separate out the values in terms of Vc1 and Vc2 and V sub I. So here we have Vc1, Vc2, V sub I isolated as individual state values, and then they're prepended by some scalar value, which is the sum of these resistances. Okay, so now let's look at the second nodal equation. So again, Vc1 is equal to V of A, Vc2 is V sub I minus V sub B. So based on this, V sub A subs directly for Vc1, Vb we sub for Vi minus Vc2. So you can do a little bit of math, move this guy onto this side, put this guy over here. That's how we come up with that value. And now we are able to do a little bit of extra magic here. So V sub B, again, we can rewrite in terms of V sub I and Vc2. And in doing this, we can cross out these values. And this negative sign here cancels out with the other one, and we get a plus sign. So that's going to give us a value of 0 at the end. So with just a little bit of rewriting, we can put all of these values together, make dVc2 look nice, and it's equal to 0. And we can put dVc2 on the other side. So now, in terms of this equation and the previous, we have the derivative of a voltage on the left and the actual voltages on the right. So we can see these here and do maybe just a little bit more rewriting. So now I can say VC1 dot and divide through by C1, and similarly VC2 dot and divide through by VC2. So an important thing to see here is that I've got VC1 all in one column here, VC2 all in one column here, and V sub I all in one column here, and on the left-hand side the time derivative of my two state variables. So this is a very common input that we'll see. We have here state values. We have here the time derivative of the state value, and we have here the input. So we can change the value of VI with a knob. The value of VC1 and VC2 change according to this differential equation here.